Good afternoon. Very glad to be here to give a talk. My name is Yunhe Tong. I'm doing my PhD at University of Bristol, working with Dr. Nikolai. Today, my topic is simulation study on evacuation strategy for vulnerable pedestrians. The title here is slightly different from what you saw on the website because we have done more work on the topic. The motivation of this research is the extensive research on pedestrian evacuation strategy basically consider pedestrians as individuals with identical characteristics. But the previous research have established that different physical and psychological conditions lead to a different ability and thus vulnerability for some individuals. Such as, according to the World Report 2011, there are more than 75 million people who need a wheelchair in their daily life. So it's important and necessary to look at the evacuation strategies to help vulnerable pedestrians. So in this project, I'm going to look at to answer these two questions. The first one is, can we develop evacuation strategy for helping vulnerable pedestrians? Second is, what factors affect the effectiveness of the strategies we developed? I just want to state that the focus on this project is not investigate the mechanism behind the pedestrian behavior, and we are not seek the optimal strategy. We just take our research as a starting point to develop strategies to help vulnerable pedestrians. To start with, we have to define what is vulnerability in evacuations. We distinguish two types of vulnerable pedestrians. The first one is distance-based vulnerable pedestrians. That refer to the people who are further away from access, just like here on this figure. You can see that the blue circles, they are far away from the exit than the red circles. So they are the distance-based vulnerable pedestrians in our simulations. So because it's related to the initial position of the pedestrians, so they kind of vulnerable pedestrians depends on the pedestrian initial distribution. And the second is we call vulnerable velocity-based vulnerable pedestrians who have lower speeds, and they should be pre-assigned. So we develop the different strategies and different evacuation stages. In pre-evacuation stage, where pedestrians have not begun to evacuate, we develop the strategies of allowing vulnerable pedestrians to respond quickly. That means they have less pre-evacuation or reaction time than others. In the response stage, where pedestrians have to decide which exit to take, which way to go, we look at the strategies of giving vulnerable pedestrians priority for exit assignment. I will talk it later in detail. And the last one is in evacuation phase, where pedestrians are moving. We look at the strategy of placing an obstacle in front of exits. I want to state that the strategies we developed here is only suitable for certain scenarios, like pedestrians can be notified and directed with 100% accuracy individually, and it can be achieved technically by modern devices in the future. We look at these strategies using modeling. We choose the social force model. It's a very popular model, and it can produce many related phenomena observed in reality. And it also have been proved as an effective tool for pedestrian dynamics Another reason I use this model is because it can offer properties which help our research, because we can look at the accumulated force between pedestrians, which is the important factors in our research. Now we look at the first example. We allow vulnerable pedestrians to rebound quickly. We call this strategy a quick response strategy. And we compare these strategies with normal strategy, where pedestrians are randomly selected equivalent number of pedestrians can move earlier, making these two strategies comparable. We look at pedestrians, we look at the scenarios with different initial position. We run 1,000 trials. That means we look at the scenarios with 1,000 different initial position. And because we look at the two types of vulnerable pedestrians, we look at the scenarios with 20% velocity-based vulnerable pedestrians. Another scenarios is with distance-based vulnerable pedestrians, because for the second scenario, the distance-based vulnerable pedestrians depends on the initial distribution. So we can't figure out how many people are distance-based vulnerable pedestrians. Now we compare the two strategies by looking at the proportion of all scenarios where our proposed strategies is better in terms of evacuation time. You can see the horizontal line here. It means if 0.5, that means the strategies are equally good. The data above this line means our proposed strategy is better. So if you look at the figure, you can see that we found no effects on scenarios with velocity-based pedestrians. That means in the scenario with only velocity-based pedestrians, our proposed strategies doesn't work. But our strategy is beneficial for crowd evacuation when distance-based pedestrians are involved. But the effectiveness decreases as the crowd size increases. Then we look at more details to figure out why it changes with the crowd size. You can see here when there is only 10 pedestrians here, for the normal strategies and the quick rebound strategy. If you allow pedestrians far away from the exit move earlier, so it certainly reduces the whole evacuation time, because the evacuation time is determined by the last person who finishes the evacuation. But when the crowd size is 18, it doesn't work well, because the people who far away from the exit, even though they can move earlier, but they have to wait anyway because the congestion near the exit. Now we look at the second strategy. We give vulnerable pedestrians priority to make exit choice. There are some important assumptions. We assume that evacuation resources are limited, and each exit has a quota indicating the maximum number of pedestrians can be evacuated. Here, for the normal strategies, these people will choose the nearest exit. So the left 5 people will choose the left one, and the rest choose the right exit. But for under the priority strategy, because here the red circle is the vulnerable pedestrian, so he has the priority to make exit choice. That means even though he is further away from left exit than the blue one, he can still choose the left one. So as a result, the blue one have to go to another exit. So that is subsequent pedestrians have to take suboptimal exit if their preferred exits have been fully used. We run our simulations and we look at different factors, including two types of vulnerability and also the proportion of the vulnerable people and also the crowd size. We can see here. We also compare the proportions of scenarios where our proposed strategy is better. You can look at the figure B. This line, 0.5, all the scenarios are below the 0.5. That means our proposed strategy is not good. Yeah. Only a small proportions are proposed the strategy is better, but overall is not good because the overall proportion is below 0.5. So we assume that which strategy is better depends on the initial distribution. So we use machine learning method to make a prediction about which strategy is better based on the initial pedestrian positions. And we can see here, in simple scenarios like D1, the highest accuracy can reach about 87%, but in more complex scenarios, it doesn't work well. It drops down to about 17%. The last example is we test if it can help improve the evacuation efficiency of vulnerable pedestrians by placing an obstacle in front of exit, which is called the obstacle effect, had been extensively studied. Just similar to last two examples, we look at different scenarios and consider different vulnerability type. And we also look at the effect of the obstacle position on the whole evacuation dynamics. And as expected, we found that overall, the placing an obstacle in front of the exit just can help evacuation in a small proportion of scenarios, and it different vulnerability type doesn't influence it. We also found that the position is very important. How well it can help improve evacuation efficiency depends significantly on the position. Here we can find this position can help the evacuation efficiency most. So summary is we can answer the questions we have at the beginning. Can we develop evacuation strategy for helping vulnerable pedestrians? Yes, we can. Certainly we can. We can develop a strategy in different evacuation stages, but they can only work in certain scenarios for certain vulnerable pedestrians. Second is what factors affect the effectiveness of the strategy we developed. The answer is the potential of strategy to improve evacuation efficiency depends on the context, like the crowd size and the pedestrian initial distribution. Thank you for your attention. Feel free to answer any questions.
Thank you. Questions? No question? One at the back. Okay.
With which parameter in the social force model did you distinguish between those two types of pedestrians in your simulation?
I just for the two types of vulnerabilities, I just change the desired speed of some pedestrians in the social force model. And for the distance-based vulnerability, I add additional process before run the social force model. I will assign their target exit. Thank you.
Anyone else? Okay.
Great presentation and interesting topic. I have a kind of suggestion or question about like the machine learning part where you deal with the prediction thing.
Yeah.
Yeah, and since like you mentioned that for some complex scenarios, some methods do not predict things well, but like for logistic regression, it is kind of typically not machine learning methods, but kind of statistical method. Or maybe if you could try to like use some statistical method or like statistical index or parameters to try to explain your models, maybe you will get some better results, or like to explain what part could be explained by the model or what part couldn't, and then maybe it's a better way for your future like prediction about the vulnerable pedestrians.
Yeah. Thank you for suggestion. Actually, I think for this example, because the scenario is very simple, and for the machine learning method, we just use simple methods because the input is only the pedestrians' velocity and their position, and the output is the building vulnerable 0 or 1 to indicate which strategy is better. So maybe I will try in the future like deep learning method, maybe. Thank you.
Great. Thank you very much.